Hello, my name is Jeffrey Campbell, and welcome to my presentation on the design and construction of a low-cost instrumented growth chamber. So, for some background, a growth chamber is a piece of equipment commonly used in plant research in order to accelerate the growth of the plants, as well as record the environmental conditions in which they grow in order to have the experiments be reproducible. However, there are some fundamental issues with the commercially available growth chambers. The first among them is the cost. This KBF test chamber is a prime example. It is a 24 cubic foot growth chamber and costs about $34,000. This can be a prohibitively expensive piece of equipment for individuals and laboratories who have limited financial resources. And compounding that is the fact that while these chambers are highly accurate and quite reliable, they are not versatile and they are unable to accept any form of third-party sensing technology. So if you want to conduct research with an unusual or novel form of sensing, such as chlorophyll fluorescence, you would either need to purchase a chamber specifically designed to do that, or you would be unable to move forward in your research. So, keeping that in mind, the goal of this project is for me to design a cheap and versatile chamber platform capable of early testing, educational outreach, and just for situations where commercial chambers are non-viable. In order to achieve this, the chamber needs to be comprised almost exclusively of inexpensive and commercially available equipment, as well as to be compatible with a wide variety of sensors, and to generally be an open source platform. So there are three primary components to this chamber so far. The first is the growth chamber itself, the environmental drivers, and the sensor nets. The growth chamber is a 3x3x6 Mylar grow tent. Mylar is the material of choice here because it is highly reflective, which gives a decent amount of insulation both to heat and to light, which is important for excluding light from the outside as well as retaining light from the lamps in the interior. The other component of the growth chamber is the PVC plenum, or air mixing box, where air will be regulated, measured, and then injected into the chamber once it is homogenized. The environmental drivers in this system are a Mars Hydro TS600. This is a LED growth lamp, which provides a decent amount of illumination for the cost, as well as having a relatively low heat discharge compared to systems such as high intensity discharge or fluorescence, which are commonly used in commercial growth chambers, as well as an Arctic King remote AC, which will provide not only cooling, but dehumidification, as well as a fan to move air through the chamber. The sensor net has three general categories. The first being the Allego Uno microcontrollers. These are very similar to Arduinos. A Raspberry Pi microcomputer, and a series of sensors which can measure CO2, pressure, temperature, humidity, and video. While only the humidity and temperature sensors are necessary in order to regulate the climate of the chamber, I have chosen to include the other sensors just to demonstrate and work on the system's ability to accept a wide variety of sensing technologies. So this is a general overlay of how the different components of the system will interact. Beginning with the environmental sensors, they will use the I2C digital communication protocol to communicate with the microcontrollers. This is the protocol I've chosen to go with because it is applicable to essentially all digital small sensors like this, as well as the fact that it allows for a greater number of sensors to be attached to any given microcontroller. Most microcontrollers are limited by the number of GPIO slots which they have on the board. However, using the I2C system, you can incorporate up to about 120 different sensors on any given board. Now, this environmental data taken from the sensors will be transmitted to the Raspberry Pi over a USB serial connection, and then two things will happen with that information. The first thing that happens with that information is that it is converted into a list of comma-separated values, which are exported to a cloud hosting site in order for the chamber's conditions to be monitored remotely, as well as just for general recording of the data. And the other thing that will happen is that data will be fed into an attenuation program, which will generate solutions for the AC unit to enact in order to keep the climate regulated. And once that air is being moved into the chamber, it will encounter the sensors again, and the loop will continue. So this is a fairly simplified diagram of how the sensors will be placed within the chamber and how they will interact with each other. There are 3 primary sensor clusters within the chamber itself, one at the air intake, one at the air outtake, and one in the middle. The air intake and outtake will be measuring CO2, temperature, humidity, and pressure, whereas the controller in the middle will be only measuring temperature and humidity. The reason for the 3 different groups of sensors is in order to get the full gradient of temperature and humidity that is present in the chamber, so that the solutions generated by the Raspberry Pi can sort of most accurately address the conditions within the chamber. However, experimental data has shown that the air outtake sensor cluster is not reliable for use in the attenuation programs due to the heat interference that is generated by the lamp. It makes it fairly non-representative. So this data is still collected, however, it is not used in the attenuation. The general breakdown of communication is described by these arrows. Red arrows indicate communication happening over the I2C protocol. Blue arrows indicate communication happening over USB. And green arrows, as you can see in the lower right corner or lower left corner of the screen, is the NEC-IR communication. This is a very common form of communication that is used by our devices, such as AC units, televisions, and stereos. So that is the protocol I have chosen to go with. That is the most broadly applicable, and also, generally speaking, the only way that you can communicate autonomously with an AC unit. So, as for the cost and construction, the current estimated cost of this project is $1,000. While the primary systems only account for about $700, the ancillary systems such as cables, GPIO pins, fasteners, and that kind of thing are a significant portion of the total cost of the project. The skills needed in order to create this chamber, I have intentionally tried to keep fairly limited in order to make this as broadly available as possible. However, in order to construct and modify the chamber, a basic understanding of soldering, as well as coding in the Arduino IDE and the Python command line, the Linux command line for the Raspberry Pi, as well as a basic knowledge of use of hand tools, especially a hacksaw in the creation of the PVC plenum. So, while things are going quite well, there is still some further work that needs to be done in order for this project to be as successful as it can be. Primarily, there needs to be improvement on the attenuation protocols that are being used. There is an issue with sensor latency, where it takes a significant amount of time for air which has been regulated by the AC unit to actually reach the sensors. And so as a result, they will intermittently over and undercompensate in terms of temperature. It creates something of a yo-yoing effect around the desired temperature. There needs to be better mounting solutions, not only for the Arduinos and sensors, but any other equipment that somebody would want to have in this chamber, such as fans or cameras. And there needs to be just further testing on the system in general to see if there are any issues that arise with extended use that are not apparent at this stage. In conclusion, I would like to thank Stephen Brewer, who has been my advisor over the course of this project, as well as the biology department, specifically Xander and his staff, for helping me acquire many of the pieces of equipment used in this project. And finally, the Walker Medical Lab, who have very graciously provided some of their grant funding to get this thing to work, as well as provided the initial need for this chamber to be constructed. This concludes my presentation, and thank you for listening.